Hi guys, welcome back to our ongoing discussion of ligand binding and specifically the idea of, excuse me, thermodynamic linkage or cooperativity in ligand binding. Now we left off last time with this discussion about Gilbert Adair, who had come up with a mathematical approach to explaining these nonlinear sigmoidal binding curves that hemoglobin displayed relative to the binding of oxygen. And he came up with this relatively simple scheme where he modeled the binding of one oxygen molecule with the associated dissociation constant, binding of a second oxygen molecule with dissociation constant. And I pointed out these were known as the Adair constants, but I left you guys with this thought that so even if this does work, which it clearly does, as can be seen when people do these kinds of experiments and fit to the Adair equation. But what does it mean? How would a molecule get 4 different binding constants if it's an otherwise symmetric molecule, which lots of information, even at the time, people had every reason to think it was a symmetric molecule. So there was absolutely no physical predictive value to this equation or to this approach or this model, even though it worked mathematically, right? Okay. That's more or less where things sat for about 30-ish years, when in the 1950s and 1960s, 2 different groups, 2 different sets of people following 2 different approaches to thinking about this problem in the 1950s and 1960s, came up with the first sort of general mechanistic models of cooperativity, right? And we're going to talk about them because they illustrate some important things, right? The first of these was known as the MWC model, or in other parlance, it was also known as the symmetry of the concerted model. And it's also, the MWC comes from the name of the 3 guys, Jacques Monod, Jeffries Wyman, and a guy named Changeux, who sort of settled on this approach to thinking about how cooperativity could work mechanistically in terms of the actual physical changes happening at the level of a macromolecule that could lead to this change in affinity that Hill and Adair had so nicely sort of pointed out. As I pointed out, this model is also known by a different name. It's the symmetry model or the concerted model. And it gets that name because the fundamental physical assumption that goes into the MWC model is that the underlying molecular symmetry of the molecule is rigorously maintained. Now, there are reasons to think this would be the case. There are lots and lots and lots of examples, both in biology and in chemistry, where molecular symmetries seem to be something that nature likes, that it's minimal energetic minimization in all kinds of systems. And so symmetries are a big deal. Nature, in many cases, works very hard or prefers symmetries, right? So there were good reasons to think that this would be a valid basis for a model. And the idea behind the MWC model goes something like this. This model postulates only 2 states of the hemoglobin monomer. There are 2 states of the hemoglobin tetramer. There have to be 2 because the affinities have to be different. One gets the name T. We'll explain why. This nomenclature, T, and its associated nomenclature for the other state, R, come from some of the work that was done structurally on hemoglobin later. But they're basically only 2 states, T and R. And they only differ with respect to the structure of the overall hemoglobin tetramer, for example, right? That yes, the individual monomers have a different structure, but they all have a different structure, right? Same with the R state. In one state or the other, they're all in that state or all in the other state. There's nothing in between, right? It's one or the other. Thus, the idea of symmetry or the concerted model. Okay. Now, the only parameters we need to make this model work then are amazingly simple. One in addition to this idea of two different oligomeric states, T and R, we have an equilibrium constant here, L, that specifies the ratio in the absence of any ligands between the T and R state, right? So specifically, it's set up thinking about the concentration of the unliganded R state relative to the unliganded T state, right? And so you can essentially, or you absolutely can think about that as an equilibrium constant. It's what it is. It describes the concentration in the absence of ligand of the R state relative to the T state, right? And for this to work, for the model to work, the assumption is that in the absence of the ligand, the R state is going to be less well populated, or dramatically less well populated than the T state. So that equilibrium is going to be less than 1. Okay. The only other parameter we need for this model to work is a parameter called C. And the C parameter is essentially just the ratio of the R state affinity relative to the T state affinity. How much better the intrinsic affinity for a single subunit of the R state compared to a single subunit of the T state happens to be. And the assumption of this model is that that is always going to be greater than 1. Right? Okay, that's it. Those are the baseline set of assumptions you need to make this model work. Two different oligomeric states, different affinity, with the R state having a higher intrinsic affinity than a T state subunit having whatever its affinity is. The R state intrinsic affinity is higher. And we have this equilibrium constant between the T and R states. And in the absence of ligand, the T state is much better populated than the R state. So the equilibrium lies toward the T state. Okay, great. So now what happens if we put all of those ideas into practice? All right, so imagine here we are, absence of ligand. This equilibrium is going to be heavily in this direction, right? Let's just establish that. Now we start to add the ligand, right? In the case of hemoglobin, it would be oxygen. So what happens now is that ligand could bind either to the T or to the R subunit, right? We know that's possible in principle. And so we have binding of that first ligand here. You'll notice, hopefully, you'll notice that we have this intrinsic affinity, the microscopic binding constant of the ligand for a T state subunit multiplied by 4. And here we have the intrinsic or the microscopic affinity of a single R state ligand multiplied by 4. Why would that be? Well, if you think back to the lecture we just had, or the part of the lecture we just had talking about macro and microscopic binding constants, you'll recognize where that's coming from. Those K sub A terms, those are the intrinsic or microscopic affinities, and the 4 is the statistical factor, right, for the first binding event. Okay, all right, so we have that first ligand bound, right? But the affinity for the R state is going to be higher than it is for the T state, so there's probably somewhat greater chance it would bind to the R state, but there's more of the T state, so that first state, right, that first binding event, it's kind of not totally clear when that might go. But if you go through the math from the assumptions of that model and you just solve the overall binding equation, the binding polynomial, what you find is something interesting, which is that the equilibrium constant between the T and the R states gets a multiplier. And that multiplier turns out to be C, that affinity, that ratio of the affinities between the R and the T state. So as one ligand is bound, the equilibrium constant between the T and the R state starts to shift. And it shifts in the direction of the R state, right? That's kind of interesting because you get multiply L by this value C. Okay, so what happens when you bind the second ligand? Okay, well there's that 3/2 times K, there's our macroscopic affinity, where the statistical factors multiply the microscopic affinity to get the second binding. Same with the T state, but now look what happens to the equilibrium constant between the T and the R state. It doesn't go up, as a multiplicative of C, it goes up as an exponent, right? So now that equilibrium between the T and the R state has multiplied by C squared. So now we get this big nonlinear drive away from the T state into the R state as more ligand binds, and so on, all the way up until the fourth ligand, the sort of perturbation in that equilibrium between the T and the R state, scales, as you see here, with this exponential that's equivalent to the number of ligands bound, right? And that has this dramatic, excuse me, impact on the state distribution between the T and the R states. Over here, at the beginning, it's going to be more T-like. And then as we bind more ligand, the conformational distribution shifts to the R state, which of course has the higher affinity, right? Okay, that's the basic idea, descriptively, of how the MWC model of cooperativity works. There's a very relatively straightforward binding polynomial isotherm that describes this binding. And there's some really good things about this model, right? It has a lot of advantages. One is that it can beautifully explain what I've just described to you guys as homotypic cooperativity, right? Where all the ligands basically are the same, like with oxygen binding hemoglobin. In the way we just went through it, this model can explain homotypic cooperativity. It can also, or I should say homotypic positive. I say positive cooperativity, right? It can also explain heterotypic positive cooperativity, right? Where, so we have a separate ligand, not the ones by a second ligand, right? Well, if that second ligand, right, were to bind to, let's use something different here. Let's say we'll call it A, were to bind to specifically the R state, that will stabilize that state. That pulls the equilibrium towards the R state. That would help drive the cooperativity in a sort of stabilizing or strengthening direction relative to our other ligand here, right? Our little square guy. Okay. The MWC model also can nicely explain heterotypic negative cooperativity, right? Where positive cooperativity, as the number of ligands bind, the affinity gets stronger, you can have negative cooperativity. And in heterotypic negative cooperativity, the binding of each ligand would get more difficult, right? So if you had a heterotypic ligand that was binding, say over here to the T state, maybe, depending on its concentration and affinity, you could pull things back in this direction, right? Which would make binding of our little square ligand more difficult, right? Okay, so that's okay, right? That's pretty good. One of the other super nice things, in addition to the fact that MWC can explain homotypic positive and negative and all this other stuff, is that it's a really simple model, right? If you actually go through the mathematics, you go through and you just sort of take a look at what things look like. The form of the equation you get out from an MWC model is independent of molecular symmetry. No matter how many subunits you've got, 2, 4, 10, 20, the underlying algebraic form of the binding polynomial or equation looks the same. It always looks the same because the underlying assumptions are independent of molecular symmetry. It's just these two states, their relative distribution, their affinity, the equilibrium constant between those two states in the absence of ligand, their relative affinities. That's all you need, right? And it can explain all these different types of cooperativity. And that minimal number of parameters, the independence of molecular symmetry, the simplicity, right? That just smells really good, right? A lot of scientists really like that kind of thing. That just has this sort of taste of something true, right? There was only one problem for this model. And that's the way this model is formulated. The MWC model cannot explain homotypic negative cooperativity. In other words, the MWC model is incapable of explaining why it is that the binding of one ligand would make of one type would then make the binding of a second ligand of the same type more difficult. and the binding then of a third ligand of the same type, even more difficult still. That fundamentally is not explainable in the context of the MWC model. Okay, so that led to a bunch of arguments about whether negative cooperativity even exists, right? It does, right? So now what? Okay, well, that brings us to the second group. And it turns out they were working at almost exactly the same time as Minot, Wyman, and Changzhou. And this was a group of guys centered around, part, Dan Koshland, who's a famous enzymologist at University of California at Berkeley. You may have heard of him, who was one of the first people, the first person to formulate or recognize this idea that the binding of ligands by proteins, and specifically he was thinking about enzymes, is not like some little solid object just whacking into something else and just fitting like a puzzle piece. That the structure of the protein changes in response to that binding event. We haven't talked about this yet in the context of enzymes, we will. But this is Koshland's so-called induced fit hypothesis in terms of enzyme mechanism, right? And what Koshland and the methane filmer did was extend this idea to the concept of ligand binding and cooperativity, right? This model is also sometimes known as the sequential model. You'll see why here in just a second. So here's our hemoglobin tetramer, now in the T state, so the low affinity state. And unlike the MWC model, the KNF model does not presuppose forced symmetry. It's not based in the idea that symmetry is maintained. In fact, specifically, it assumes that's not true. So what happens, we have that first binding event. That case of A now would be binding to a single subunit. And there's an associated, in addition to the binding, there's an associated, you'll notice, a conformational change of that one subunit that is bound to ligand, right, into the so-called R state, but it's just that one subunit. But you'll notice the way this is drawn, what those shape changes are supposed to indicate is that when this one subunit binds, it induces structural changes in the neighboring subunits in the oligomer, right? So-called strain is the way it's often described, builds up in those neighboring subunits, sort of like it's pushing them towards the higher affinity state. Maybe not there because it's only one, right? So the feedback is going to be very much in the direction of, pushing back the other way, which is why the affinity, this first binding constant, is going to be low, right? Because there's only one ligand bound, and the feedback is going to sort of try and push that ligand, try and push the molecule back in this direction. Okay. All right. But now what happens in the second ligand binds? Well, you can sort of see where this is going, right? Second ligand now drives the one that was closest to a square, closest to the high affinity state. It now locks this guy up in that state, right? And look what are happening to the other guys. The strain that's building up as a consequence of the ligand's binding continues to push those subunits into the fully high affinity state. So the idea that the induced conformational changes build up in the oligomer without an imposed requirement for maintaining symmetry, the fact that you specifically don't maintain symmetry, now generates, if you think about it, it's recreated the Adair model that we just talked about. We've got the series of binding events, right? Lost communication there for some reason. There we go. We have this series of binding events, right, that have occurred. Each one associated with one ligand binding. And we have something that mathematically is going to look very much like the Adair constants, but now we have an explanation. There's now a physical molecular explanation for why and how an initially symmetric molecule could generate 4 different individual intrinsic affinities that increase in strength, all right, as you add the number of ligands. All right, so that's now hopefully see why this is known as a sequential model. So the KNF model has some advantages. In addition to the fact that it is significantly more flexible than the MWC model, it absolutely can explain homotypic negative cooperativity, right? Which MWC can't. So the KNF model has a greater capacity for explaining a wider range of cooperativity phenomena than the MWC model can in principle. The problem that sort of crops up, though, that flexibility sort of comes at a cost, which is that unlike with the MWC, the form of the binding equations of the KNF model all depend on the molecular symmetry. You get this sort of, you need essentially an Adair constant, you need an intrinsic affinity for every state of the partially liganded states of the molecule. So the algebraic form of these equations is a function of how complex your molecule is, right? And so they can be highly complex, right? So that put some people off, that the loss of simplicity that came with the MWC model. And yet there is this observation that it can explain things MWC can't. All right, well, when you get down to it, right, which one's right? Is either one of them right? Well, what do? Right, you got a model. So the next thing you do is you go and you apply it to some data, right? So in our case, we're talking about hemoglobin. So let's go apply them, take some data. These two models have these different equations, apply them, see what happens. That's what happens. Both models fit. Hemoglobin's cooperative, that nonlinear sigmoidal binding curve, the symmetry model and the induced fit of the sequential model work equally well. Within the noise of the measurement, you cannot distinguish them. So from the point of view of what we've been sort of doing, having you guys do working problems, just model fitting to the data doesn't distinguish. And these two models, if you think about it, have fundamentally different assumptions. They're saying very different things physically about what's going on. But the model fitting doesn't distinguish them. So what do you do?